Alrighty, hey everybody. So I'm Nick. Met quite a few of you guys before, but if I haven't met you before, I'm the guy sending you emails and organizing most of the things. Tyler's my co-organizer, who's also presenting tonight. In terms of general announcements, Summit's coming up, almost a month away, maybe a month away exactly. So it's in September. If you're interested, go sign up. There's free tickets and there's priority tickets for $100, and I think if you use this code, you get 25% off. So check that out if you want to come to the summit. It's always really great. Been going for 5 years now and hasn't disappointed yet. We don't have next month's meetup scheduled, so if anybody would like to talk, or if anyone has any suggestions for a talk, please send them my way. It's like 5 days before the summit, so I don't know how involved of a talk will do, but we'll see what we can get going. Besides that, still some pizza and drinks and t-shirts in the back. Didn't get any, so get those. And yeah, here's Tyler. Oh, before Tyler, I always forget at the end. So at the beginning, who needs a parking validation if you parked in the Omni parking lot? 1, 2, 3, 4. Just 4. Okay. Here's Tyler.
Nice. All right. Thanks everybody for coming out. So my name's Tyler. I work at DataStax with Nick. I work on Cassandra itself. I've been working on and around it for about 5 years now. I'm familiar with most parts of Cassandra. I primarily work on driver-server interaction and the query language, but I've kind of touched most parts of the code base over the years. So I'm going to try to explain the read and write path. So I'm doing a couple of things different in this talk. The first is that it's being live streamed, and I'm going to attempt to take questions from anybody that tweets questions during the talk. I have no idea if anybody's actually going to do that or if anybody's watching at all. But if they are, maybe we'll get some questions there. The other thing is that I really dislike PowerPoint, so I decided to completely forgo PowerPoint. The last talk that I did it all in Vim. So this one is like not quite so sparse. I actually drew out some diagrams, but we'll see how this presentation style works. I haven't tried it before. Hopefully it works out well. All right, so the actual talk. This is it's mainly targeting users and operators of Cassandra. So I'm going to explain things at sort of a high level. I don't want to just talk about code necessarily, but I want to describe all the concepts. So the goal here is if you know more about how Cassandra works internally, that helps you to pick a better data model, helps you to tune your cluster for better performance, helps you to diagnose problems. So I'm going to try and give you that sort of level of information that's useful there. All right, let's begin. So for any sort of read or write request, there are basically 3 main stages in Cassandra. You've got the driver, the coordinator, and the replica. So with Cassandra, the driver is quite a bit more important than it would be for interacting with most databases. Since Cassandra is a fully distributed database, and it's designed to be very fault tolerant, the driver needs to be able to talk to all the nodes in the cluster, deal with them going up and down, all sorts of special considerations. So knowing how the driver interacts with Cassandra is actually pretty important if you want to get the most out of your cluster. So I will talk a little bit about how the driver works as part of this talk as well. So I'm going to start out by talking about this part here, and specifically about the write path, because the write path is a lot simpler in Cassandra than the read path is. All right, so the driver. The driver normally maintains a connection to every node in the cluster. The main exception to that is if you have a multi-data center cluster, then it's normally only going to connect to nodes in the local data center. So whenever the driver goes to execute a query, it needs to decide what node to send that query to. It has the option of sending it to any node in the cluster. Any node can be a coordinator. So kind of the most basic approach the driver can use is just to do a round-robin distribution of queries. So it just goes through its list of nodes and picks the next one on the list for the next query that it needs to execute. But it can be a little bit smarter. If we want to try to ensure that these are the same node and skip a network hop, we can basically do what Cassandra does to figure out what nodes are replicas for a row. So the driver can introspect the query that it's executing, and it can look at the partition key, and it can run the same hash on it that Cassandra does. And then based on its knowledge of what nodes own what tokens in the ring, it can figure out what nodes are replicas for that row. So that allows it to pick a node that's also a replica to be the coordinator for the request. So this, in some cases, like if you're using consistency level 1, that'll save you an extra network hop. So that cuts down on latency, it avoids a lot of serialization, and so it can really help latency and throughput. So in the drivers, at least the DataStax ones, that's called the token-aware load balancing policy. So the driver, it picks out a node that it wants to send the query to, and then it needs to send the message. So what is it actually sending? So there's kind of two styles of messages that the driver can send to Cassandra. There's unprepared statements and there's prepared statements. So unprepared, it's basically just sending a CQL query string, just like if you typed it into the CQL shell. So to do this, the driver takes the query parameters, puts them into the string, and just sends off a string to Cassandra. So when Cassandra gets that, it has to parse the query string, convert it into Java objects that represent the query, and then it can actually move on to executing the query. So for a little bit more efficient version, Cassandra has prepared statements. So the driver sends off this query string without putting any query parameters in there. There's just the placeholders. And Cassandra will parse the query, create those Java objects, but then it caches them internally. And it stores them in a map that's keyed by a hash of the query string that it parsed. So the reason it uses a hash of the query string is so that no matter which node you prepare the query against, it's always going to have the same ID. And Cassandra passes this ID back to the driver. So when you go to execute a prepared statement with the driver, it just needs to send the ID and a binary representation of the query parameters, which is quite a bit more compact. So the driver, so there's a couple of steps to query preparation. First, it just prepares it against one node to make sure that the query is actually valid. Once that successfully happens, the driver in parallel prepares it against every other node in the cluster. So every node has this prepared statement stored independently, but it's the same ID on every server, so the driver can use that ID wherever it wants to. So basically the lesson here is if you execute a query more than a few times, make sure you prepare it. It saves a lot of extra work. All right, so the driver, when it sends request to Cassandra, it picks out a request ID for that request. The request ID can be any number between 0 and 32,000, and it just has to uniquely identify that request within that connection. So only one request can use a particular ID at a time on the connection. So the driver, essentially, it fires off this request with the request ID, and then it waits to hear, it starts an event loop, and waits to see, it waits to get a message back from Cassandra. So Cassandra is free to respond to any of these requests in any order that it wants to, and the response includes the request ID so that the driver knows which request it's getting a response for. So the couple of nice benefits to this are that the driver can easily execute queries asynchronously. So it can just fire off 100 queries and then wait for them all to come back at once. So all of the drivers have a very nice asynchronous API as a result. It allows thousands of operations to be executed concurrently with a single connection. So the drivers don't need to maintain a lot of connections. And Cassandra can also respond out of order. So if you send a really large operation followed by 10 small ones, it can respond to the 10 small operations before it's finished handling the large request. This did change a little bit in Cassandra 2.1. Before that, each connection could only have 127 different IDs. Since 2.1, it's 32,000. So if you're using an older version of Cassandra, the driver might be using more than one connection per node. All right. So once the driver has sent off this write request to the coordinator, what does Cassandra have to do with it? So the first thing that it does is it needs to figure out what nodes are actually replicas for that request. So it does that whole hashing business, looking at the token ring. It figures out what nodes are replicas. So we'll say this one right here is the coordinator, and these two are the replicas. The first thing it does is it looks at the consistency level that you used and figures out how many of these replicas it's going to need to get a response from. So say it needs to hear back from both two replicas based on the consistency level. What it does is it checks the failure detector to see if any of the nodes are already down, any of the replicas are already down. So if one of the two is down when the request comes into the coordinator, it can see that it's not going to be able to meet the consistency level, and it immediately fails the request with an unavailable exception before it does anything else. So it's a really quick failure in this case. So normally, that's not the case though. And the coordinator will go ahead and fire off the writes in parallel to all of the replicas. And then it waits for responses. So if you have a consistency level of 1, it only has to wait for one of those nodes, the replicas, to respond before it can respond to the client. Say one of the replicas does respond, but the other one dies while it's handling the request, so the coordinator never hears back from it. What it does at that point is it stores a hint locally on its own system. So the hint is basically a record of the mutation. So it knows that this node was down during the request, and whenever it comes back up, it needs to send this mutation to that node again. So the hint doesn't really provide any sort of consistency guarantee because there are limits to hinting. They're not stored forever. But it does help to, if a node's just down for a brief amount of time, it helps to restore consistency more quickly. So coordinator's in charge of dealing with hinted handoff. Say if both of the replicas failed to respond, they both died in the middle of the request, then of course it'll just send a timeout exception, a write timeout exception back to the client. All right. I think that's everything I wanted to talk about there. So the multi-data center coordination is pretty similar, but there's only kind of one twist to it. Oh. Yeah, sorry, this thing has like touch sensitivity, and it's kind of easy to trigger it. Okay, so say this node's our coordinator again, and as usual, it will write directly to the local replicas. But for the remote data center, in order to minimize the cross data center traffic, it picks out one of the remote replicas as a remote coordinator. So instead of sending the write directly to all of the replicas in the remote data center, it sends a special forward message to this node, which basically lets it know that it needs to send the write along to the replicas in the other data center as well. So this, like I said, this is just to save cross data center traffic, essentially, to minimize it. The replicas in the remote data center do respond directly, that's a horrible line, but to the coordinator. So it's only kind of on the outbound where this remote coordinator is used at all. So multi-data center it's actually pretty simple in terms of how it works in Cassandra. All right, any questions so far? Yes.
And does it wait for all this to happen?
Does it? Yeah, so
waiting as well?
That's a good question. So it's very configurable how much you want it to wait. Depends on the consistency level. So there are consistency levels that are specifically designed for multi-data center environments. So there's, for example, there's local quorum. So say if you do a write at local quorum, that means that it needs to wait for a quorum of the replicas in the local data center. So say these two, but it doesn't need to wait for any acknowledgement from the remote data center. So the nice things about that is you're always writing to every replica, no matter what your consistency level is. But you can get strong consistency within the local data center. So you can get guarantees about reading your most recent write within a data center, but you don't have to pay the latency cost for dealing with a remote data center. You can use other consistency levels for guarantees if you want to make sure that you've, say, written to the remote data center or are reading from it. There's each quorum, which requires a response from a quorum of nodes in every data center. You can also use consistency level all to wait for a response for all of them. There's also local one. There's a few options, but basically it's configurable whether you want to wait for acknowledgement from the remote data center or not.
And if I may, the second question would be, is there a timeout value also? I guess you call into the RC.
Yeah.
Is there a timeout value before it hears for responses from the other guys?
So
for each one of them, if you need them?
Yeah, so this, the original coordinator deals with all of the timeouts itself. So basically it sets up internally a bunch of callback hooks. So it's waiting for responses. Those have a timeout counter set on them, or a certain time when they're going to expire. And if that time passes, then the coordinator goes ahead and stores the hint, or if it's seen enough timeouts to where it knows that it can't meet the consistency level, it responds to the client. So all the timeout handling is done by the original coordinator. The remote one is really only to forward the mutations.
I guess it's kind of piggyback on my question to say that in hinted handoff for the remote coordinator, since you're waiting for the responses directly from the nodes, so the original coordinator will store the hints, and so if you have to use hinted handoff, you're actually not getting the advantage of the cross DC.
I believe that's correct, yeah. So
you're going to forward it, well, when it comes back online, you'll send it directly with the hinted handoff.
Yeah, so just to clarify, Jeremy is pointing out that in the case of replaying stored hints, those will have to go repeatedly over the cross DC link because it's the original coordinator that stores them, not the remote one.
And the return and the response is going to be a small message, so I don't know if that's...
Yeah, the right response is a small message.
Yeah, so I don't know if that's significant. I didn't realize that it would send it back directly from the nodes and then the hinted handoff manager from the coordinator. So that makes sense. I didn't know if there's special handling, so that's good.
Cool.
Are you going to go over the read path separately? Or?
Yeah, I'll do that after the write path. All right, any other questions about multi-data center stuff? No, okay. Damn it.
one thing that may be confusing, just I don't know if people are thinking this, but the remote coordinator, it's per operation, so it's not like that's a special role that plays or is a point of failure or anything like that.
Right. There are no special roles in Cassandra, so this is all chosen as part of the request.
So I guess follow-up then. So the remote coordinator who happens to be picked is down. That means you'll never get an each one.
So the original coordinator will not pick a remote coordinator that it knows is down. Right. It'll look at the failure detector before it picks one. If the remote coordinator goes down, say during this transmission, then it won't get any acknowledgments from the remote data center at all. So if your consistency level doesn't specify that you need to wait for some sort of remote data center acknowledgement, you won't even know about that, right? Of course, you'll have monitoring, so you know that data center is having problems and you need to run repairs. But as far as that particular write operation is concerned, it can still succeed.
It won't store a big handoff or something to send to the.
It will store hints, yeah. It'll store hints for all of those remote replicas, because say if there's 3 in the remote data center, it didn't get acknowledgments from any of the 3.
Yeah, okay. It's quite an edge case.
Yeah. So I think what will happen in that case is it'll try and replay the hints almost immediately because it still thinks the nodes are up, and those will succeed, and so it'll delete the hints locally. So that should resolve itself pretty quickly. All right. Any other questions about multi-data center stuff? Cool. So batches. So there are 2 kinds of batches. The diagram here is for the more complicated version. So there's unlogged and logged batches. So unlogged is basically you're just cramming multiple writes into one message. Cassandra doesn't really specify any strong guarantees about what happens with unlocked batches. It's basically just, I want you to do all these writes, and that's about it. There's a couple of small isolation guarantees, but usually you don't care about that. So the more complicated cases, something called logged batches. They're also called atomic batches in some places, but I think that term's really confusing, so I like to call them logged batches. The purpose of logged batches is really to ensure that if you write, if any part of a batch write succeeds, eventually the other parts of that will also succeed. So that some definition of atomic, but it's definitely not isolated, and people usually kind of mix the 2 concepts. So the way that Cassandra makes this guarantee is the coordinator, before it actually writes to the replicas, it first picks out a couple of batch log replicas. All right, I really have to stop doing that. That's crazy. All right, so these are the batch log replicas. Basically what it does is it tries to pick 2 nodes that are in different racks, but are in the local data center. So it's kind of trying to have the maximum durability without paying cross data center write cost. So it essentially writes the entire batch out on these 2 nodes in different racks. And once it hears that those have both successfully been written, it then proceeds to write out the normal mutation to the actual replicas, to these guys over here. If that succeeds, the coordinator tells the batch log replicas that they can go ahead and delete that batch log entry. If the write does not succeed, say the coordinator goes down in the middle of actually executing these writes, then the batch log replicas will not delete that batch log entry, and they'll know that they need to try and replay that entire batch until it completes successfully. So there's not any sort of strong guarantees about how quickly that will complete. I think the batch log replay is periodic. It's like every, I don't even remember, every 10 minutes or something, it tries to replay it. But essentially, this is designed to deal with the case where the coordinator goes down after having written some of the entries in a batch. So there's definitely some extra cost here, but if it's very important that you eventually write all the contents in a batch, this is something you want to use. All right.
Can I just
Yeah.
add something to that? Batches are not meant as a performance.
Yeah.
Performance.
Yeah, I
A lot of
should
people
point that
do
out.
Yeah.
Yeah, a lot of people use batches as a way to make things go faster, get higher throughput, and so they'll put thousands of inserts into one batch. So what that does is it means the coordinator then needs to create 1,000 different mutation messages, calculate the replicas for all of those, handle all of the dispatch and the callbacks, and it takes a long time to process those thousands of operations. So the coordinator has a ton of objects on its heap during this time, which tends to cause garbage collection pressure. And it also means that if any one of those operations fails, it's going to send an error response back to the client. And if your client's not smart about it, and it can only really be so smart in this case, it's going to retry the entire batch, right? So even small failures can kind of cause a cascading failure scenario if you're using batches with thousands of operations in them. So
You're better off just going straight.
yeah, you're better off relying on those nice asynchronous writes that the driver has. The one decent use case for batches is if they're all in the same partition, because the coordinator will end up just sending one message to one set of replicas, and it's roughly as efficient as just doing a single write to a partition. So that does actually save you some serialization and network overhead. But don't try and use batches that span multiple partitions as a throughput optimization. So, question in the back? Does it? Okay, cool. Yes?
I may be going off in the weeds here, so take this off. But what if you said that in any given transaction, if you will, or request, any of these nodes could be a coordinator.
Right.
So what if the coordinator goes down in one request, and then some other coordinator gets a request to update a row that basically puts the writes at conflict? Does that make sense?
Yeah. So that's all about knowing how to work around essentially a lack of transactions in Cassandra. So that's something that basically you either build into your data model, how you handle those sorts of conflicts, or you're okay with the last write wins conflict resolution.
It's just something. So it's something that can happen.
Yeah, absolutely. It's something that you need to be aware of and plan for.
Okay.
All right. Any other questions on batches? Yeah.
Yeah, when the batch is being replayed, who plays the role of the coordinator? Because now there's two guys with the batch logs. Do they both wake up and try and?
Yeah, I think they both do. I think it's, I want to say that it's like a slightly randomized loop or something, so that maybe they won't do it at the same time. So the nice thing about writes in Cassandra is that they're idempotent, right? So every write comes with a timestamp. So if you replay the write and there happens to be newer data already written, it'll basically ignore what you wrote because it has a lower timestamp. So the one exception to idempotent writes are counters, and counters aren't allowed in log batches. So probably for that exact reason.
If one of the batch log coordinators succeeds, does it tell the other one to delete its batch log entry?
Don't know. Probably not. So I had to just guess.
Some right overhead that you would get.
Yeah. It might get written twice, but that's writes are pretty cheap in Cassandra. It's not too big of a deal.
Well, you mentioned timestamp, and just thinking about that, I mean, do you have to do some type of, is it on the cluster to manage its time syncing, or is that part of Cassandra as well?
So you do want to run NTP on all of your machines, just as a generally good advice, but even with NTP, you can't rely on exactly precise timestamps. So essentially, if you're worried about less than like a second of drift in clocks causing problems, you need to design your data model to deal with that case of clock drift. So normally you'll use things like essentially unique primary keys for everything that you insert to make sure that you don't overwrite something.
While we're on this topic, the timestamp you're talking about, where is it generated and when? Is it generated at the coordinator or at the actual place where it writes or at the driver?
Yeah, that's an excellent question. So it can be generated, there's actually 3 places it can come from. I'll say what my preferred one is. Preferred one is to let the driver generate it for you. So in Cassandra 2.1 and higher, the native protocol supports sending a timestamp alongside the write. I'm not sure how all the drivers treat this, but at least the Python one, if it's talking to Cassandra 2.1, it'll automatically generate the timestamp client side just before it does the insert. And that's nice because it has microsecond precision, and it knows the timestamp if it needs to replay the operation if it fails. That works pretty well. You can explicitly specify a timestamp as part of the CQL query as well, with a using timestamp clause. And then last, my least preferred source of the timestamp is to let the coordinator pick it for you. So if the driver didn't set one, and if it's not in the CQL query, then the coordinator will automatically pick one. So that the main downside to that is that the client doesn't know what the timestamp is, so it can't retry writes with the same timestamp. And Java doesn't have high resolution on its clock. It has millisecond resolution. So occasionally you can have problems where if you have your client doing writes in a loop, just a fast loop, and you try and overwrite something, you might overwrite it within the same millisecond as another write. And if you do that over 2 separate connections, then your second write might not ever show up because it's using the same timestamp. And Cassandra only tries to deal with overlapping timestamps within a single connection. That's kind of complicated to explain, but that's timestamps. Okay, cool. Any more timestamp questions?
And this is and it's different from key value stores because Cassandra has a richer data model, and so the timestamp is going to be to the actual cell that you're writing to.
Right.
And so if you're overwriting things in a different cell with the same timestamp, then it won't matter because you have the width to the row or the partition.
Right.
That makes it much less likely to happen.
Right.
So it's even more of an edge case.
Yeah, you have better tools for dealing with it than you would with, say, just a basic key value store. Just from a data modeling perspective. Okay. So now we get to the last stage of the writes, and this is what actually happens on the replica. So the write comes in, the first thing that happens is it goes to append it to the commit log. Commit log is all about durability. And commit log is also to help ensure sequential I/O. It's part of the sequential I/O on writes architecture of Cassandra. So commit log is append only. So it's constantly getting new writes appended to it. And the commit log, there's a couple of different modes for it in terms of how often it is synced to disk, how often a fsync call is explicitly made. And the default one is periodic, and I think by default it syncs every, is it 10 milliseconds, 100 milliseconds?
I thought it was 10 seconds.
10 seconds? Yeah, it could be 10 seconds, I don't remember. I would probably lower that on my own production cluster if I had one. But basically, fsync is called every 10 seconds to ensure the write's durable. The reason that that's the default is that normally you're writing to multiple replicas, and the odds of all of those replicas failing within that 10-second window is pretty low. So usually that's a reasonable durability guarantee. But if you need better guarantees than that, you can use the batch mode, which essentially collects writes for a little while and then f-syncs them all before responding. So that way, it's essentially guaranteed durability at this point in the write stage. So the commit log it's broken up into segments, and each segment I think is like 64 megabytes, and it stays around to ensure the durability of the write until that write can be written out to disk in the form of an SS table. Somebody looking for somebody.
She's the meetup coordinator at Capital Factory. She's just
Okay. Okay, cool. So the commit log segment stays around until every entry in it has been flushed to the disk in the form of an SS table. And so normally this commit log segment can have writes from a whole bunch of different tables in it. So usually it requires flushing a lot of mem tables to disk in order to free up the commit log segments. So I'll talk a little bit more about how that all works in a second after I talk about mem tables. So after the commit log, the replica updates this in-memory structure called the mem table. The mem table is basically a giant map, and it's keyed by partition keys. So it's kind of one big entry per partition, and it uses something called a concurrent skip list map, which is a pretty cool data structure. If you're not familiar with it, I recommend reading up on it. And then within each partition, it's basically a B tree of rows. And by default, Cassandra is kind of optimistic about there not being conflicting writes within a partition, or concurrent writes, I should say, not conflicting. So normally it'll just try and do a kind of a copy on write, replace the entire partition at once. If that fails too many times, it switches into a sort of a locking mode. So you can get different performance characteristics based on whether you're doing a lot of updates to a partition at a time or not. Eventually this mem table gets flushed out to disk to become an SS table. And the SS table is structured very similarly to the mem table. There's a couple of things that can trigger the flush. The first thing is Cassandra starts to run out of memory space to store the mem tables. So if it sees that the mem tables are taking a certain amount of space that's getting close to the limit, it starts to flush out the largest ones. The other condition that can cause flushes is the commit log. So eventually the commit log will also hit its limit in terms of space, and it'll recognize that it needs to start deleting the oldest segments. It can't delete a segment until all of the corresponding mem tables have been flushed to disk. So it goes through and it starts to trigger flushes of all of the mem tables that it needs to until it can free up the segment. So that's basically the two flushing conditions for Cassandra. Yes?
What's SS stand for?
Sorted, it's either sorted string or string sorted table. Sorted string? Yeah. It's a term from Google Bigtable. It's not a very good name, I don't think, but
it's sorted. I mean,
it is sorted,
makes sense.
yeah, and I don't know what string necessarily means there. And the main thing to know about SS tables is that they're immutable. That's pretty much the only property you care about. I'll talk a little bit more about how they're organized as part of the repath, though. Somebody else had a question, I think. Jeremy? No? Okay.
Is there a time frame where just like every half an hour or so, every mem table eventually will get flushed if nothing's happening? Like an idle cluster, will it ever flush?
Yeah, no, it should not. Not in recent versions. In old versions, it used to, but not in any recent versions, no. The reason it wants to avoid flushing for as long as it can for a couple of reasons. The first is that if you overwrite anything in the mem table, it gets merged in memory, and it only needs to write out the most recent version to disk. So for a lot of things, a lot of use cases, updates are most likely to happen shortly after something's created. So the mem table tends to absorb a lot of overwrites. The other reason you want to hold off on flushing as long as possible is you really want it to be as big as possible, and so that you have as few SS tables to deal with as you can. The more SS tables you have, the more you need to compact, and the more SS tables a read needs to touch. So the fewer SS tables, the better. So that's why it tries to hold off on flushing as long as it can.
So the replica goes down when you only have contents in the mem table.
Yeah.
Can you recover that?
Yeah, absolutely. Cassandra is definitely designed to handle that, and that's what the commit log is all about. It's the durability aspect of it. So on startup, if that happens, Cassandra reads through the commit log and replays all of those mutations. That's the first thing it does before it starts accepting any requests.
Doing larger writes is a good thing as well from a storage perspective, because you get the best performance out of storage by doing a small number of larger writes.
Yeah, exactly. Lots of large sequential I/O. It's a good point. All right, so any other questions about? Yeah.
Sorry. About SS table size versus count. Is there like a size of SS table that's prohibitive, or versus like in size to your compaction anyway? That's.
Yeah. I'll say that it depends on the strategy, compaction strategy. In general, no, there's not necessarily a prohibitive size. It's more about kind of the balance of sizes for most of them. But I don't want to talk about compaction too much during this talk. So yeah, I'm not going to, there's a lot of things I'm not talking about: bootstrapping, repair, compactions, and so on. So otherwise, I will never finish this talk. All right, anything else about mem tables or commit logs? Everybody has mastered them. Okay, so the last things to do on the write path for the replica is it needs to update the secondary indexes. So it just sends them a notification that there's either a new row or an updated row based on what it already had in the mem table. And then it needs to invalidate any row cache entries. So the row cache is validated on writes, it's not updated on writes, which kind of sucks, but that's the way it is right now. And then once all that's done, the replica responds to the coordinator. All right. Read path is next. Anything else about writes?
Quick question, how big are those tables, the mem tables in memory?
How big are they? Yeah, so the total space allocated for mem tables is by default like a quarter of the heap size. Normal heap size is 8 gigs, so normally you have about 2 gigs worth of mem tables. That's all configurable. They can be stored on heap or off heap, or partially off heap. So if you store them off heap, they could be a little bit larger. The minimum size for a while was 1 megabyte, but I think they were recently shrunk. The minimum size was shrunk, so they can take up a lot less space now.
So it sounds like you're at the largest, you're multiple gigabytes. Do you write out multiple gigabytes every time you flush? Or is it just?
Yeah, right, yeah, it would write out the entire 2 gig file. And that'd be awesome if your smallest SS table size was 2 gigs. That would be excellent. Normally they get flushed at a lot smaller size, maybe a few megs or 100 megs is more typical. I guess if you just had one table and that's all you used, then it could be a couple of gigs. Anything else? All right. Are y'all's brains like fried yet? Is this like super dense information, or it's going pretty well? Okay, cool. Read path. This is more complicated than the write path, but I already covered some of the concepts, so it should work out pretty well. All right, so the read path. Back to the coordinator. I'll talk about a little bit about how the driver deals with reads, but there's only a couple of interesting cases there, so I'll wait later for that. So the read path, the coordinator has to do a few things differently, or gets to do a few things differently. So with writes, the coordinator always needs to send the writes to every replica, but for reads, that's not the case. So the coordinator can be smarter about which replicas it talks to. So it uses something that's called the snitch to determine which replicas it actually wants to request data from when it's handling a read. So the snitch, normally say if you've got like a multi-data center environment, it will prefer nodes in the local rack. And if those are all down, it'll prefer nodes in the local data center. And if those are all down, it'll prefer nodes they're in a remote data center. But Cassandra wraps all of so the snitch is configurable, so you can change what replicas it prefers. But Cassandra wraps any snitch you use with something called the dynamic endpoint snitch. So the dynamic endpoint snitch is designed to essentially pick the replica with the lowest latency. So it prefers whatever the underlying snitch says, unless that preferred replica has latency that is considerably worse than some other replica, in which case it will sort of override that choice and pick the faster replica. So what normally happens is if the coordinator is a replica, the dynamic endpoint snitch picks itself to handle the read, because it's almost always going to have the lowest latency when it's talking to itself. I can't remember what I was supposed to do with this diagram. It's probably not useful. So I think that's everything that's kind of useful to know about the snitch. That is one reason why sometimes if you watch your metrics closely on a cluster, you'll see that some nodes have a lot higher local read count than others. And the reason that happens is the dynamic endpoint snitch, it'll start using one replica for a lot of queries. That replica starts to get a very warm cache, and so it gets lower latencies for its requests. And so it's like a positive feedback loop. It's preferred for more and more requests. And as long as it can keep up those really low latency responses, it'll continue to be the preferred replica. If it then starts dealing with a large garbage collection or a big compaction or something, then maybe its latency will spike and another replica will start handling a large number of requests. But you might see that if you watch your metrics closely.
Does every message go the fastest, or does it send out like some small portion of traffic to kind of sample the others?
Yeah, so it does occasionally try out other replicas. I think it's like every 10 seconds. Probably configurable through some kind of obscure flag, but yeah.
How does it sample the latency? Is it getting from other snitches? Do snitches share their latency? It's hard to say.
Do snitches share their latency? No. It basically just, I think every request updates a histogram of response times for that node. I don't think it's even on a per table basis. I think it's global. No, the snitches don't really interact at all.
You just have a single snitch that kind of informs you it's a snitch called the snitch because it's snitching on the topology of the cluster,
Yeah.
and then the dynamic snitch will enhance that with the histogram information for the modifier, basically.
I think a lot of latency has to do with network topology, so that we can
Relative to every other node, right? So sharing may not make sense.
Yeah, and the connections exactly,
Yeah.
between them, or like you have a router line or something like that. And I don't know, and this may be obvious, and you may have covered it at the beginning, but the token aware nature of the driver. So the driver has a way to it has a control connection to the cluster, and so it'll discover the topology of the ring when it starts up the connection. And so it knows where all the tokens are stored. So if you're reading or writing a certain record, it'll go right to one of the replicas for that record, so you don't have to have a coordinator that's separate from the replica set.
Right. All right. So, when Cassandra's dealing with the read request, the coordinator doesn't ask every replica that it needs to talk to for the full set of data. So say we have replication factor 3 and we did a request at all, so it needs to talk to all 3 of these replicas. It'll only send a data request to one of them. And it picks the one to serve the data request through that whole snitch process that I just talked about. And the other ones get something that's just a digest request instead. So those replicas, they go through, they read everything just like they would normally do, but then they just take a hash of it and send it back to the coordinator. So when the coordinator gets these responses, it will hash the data response and check that it matches the hashes from the other nodes that responded. So since Cassandra's eventually consistent, these won't always match up. So if one of the digests or the data doesn't match, Cassandra will reissue a full data read to all of the replicas that it talked to, so that it essentially gets the latest version of the data from all of them. And it will compare that data to see which replicas have out-of-date information. And then it'll do something called read repair to correct that inconsistency. So it'll send the most recent version of that data to the nodes that have out-of-date information. Read repair, it always happens in a blocking fashion whenever your consistency level specifies that you have to read from multiple replicas and there's this mismatch. So in the example I just gave with consistency level, all of that read repair process would happen before the coordinator responded to the client. Say if you're only reading at consistency level 1, normally it's just one replica is sending a data response and that's it. But there's a configuration parameter called the read repair chance, which can cause these extra digest requests to be sent randomly to kind of help repair inconsistent data in the background. In that case, it doesn't block the request. It's all kind of asynchronous after the fact. All right. So
if you have to read all the replicas, this whole stuff, the stuff you were about earlier about the snitch picking the best one, becomes null and void because you have to wait for the slowest one.
Right, but almost nobody reads at consistency level all. Okay. It's much more common to read at either 1 or at quorum. Okay. So at 1, it's particularly important because you only have to wait for the fastest replica. At quorum, you can at least avoid the slowest replicas, and you can send the data request to the fastest replica. Right. So there's kind of a cool feature in Cassandra 2.0 and later called rapid read protection. So say we are reading at consistency level 1, and these are my latency numbers over here for the replicas. It picks the one with the lowest latency. It's just 1 millisecond. It sends it a data read. But say this node starts doing a GC or a dies or something. The coordinator is going to have to wait until the full timeout before it can send any sort of response to the client. And normally your timeout's going to be something like a second, right, or maybe higher. One of these other replicas could potentially serve that read really quickly. So what rapid read protection does is, if it's sent out the read and it hasn't heard a response within, say, the 99th percentile of expected latencies, it will send a redundant read to the next fastest replica. And so what can happen is this replica could respond really quickly, and then when this one's done with its garbage collection pause, maybe it'll respond too, but the coordinator's already responded to the client at that point. So rapid read protection it's really designed to help minimize 99th percentile latencies. So it helps deal with garbage collection pauses, especially and other kind of transient effects like that, or even with the node going down. Normally, without this, if a node went down, you would see all of your latency spike and your throughput dip until all of the other nodes figured out that it was dead, right? But this helps out with any requests that are going on while that node dies, if that makes sense. And that's configurable as well. So it can go anywhere from 99th percentile, which is the default, down to like 75th percentile. So you have some options there, depending on how latency sensitive you are. Okay, range queries. So what happens when you do select star from my table? Normally that's, this is like the first thing that everybody does when they start kicking the tires with Cassandra. They insert one row and then they run select star, and they want to know why it takes like 50 or 100 milliseconds to answer this when it's really fast in a relational database. So that's pretty much the worst query that you could ask Cassandra, and I'll kind of explain why. Whenever the coordinator gets a request for a range of partitions or a range of rows across multiple partitions, it needs to essentially go through and it will read all of this range, and then it will read all of this range, and so on until it hits whatever.
Apparently there's one over.
Oh, Amber.
Oh, okay. I was gonna say, I hope it's not a tornado with all this glass around. That would be awesome. Okay, so yeah, so normally it'll go through and it'll have to read all of these ranges, and each range requires a separate command from the coordinator until it hits whatever limit you specified. Default limit for a page, and I'll talk about paging in a bit, is 5,000 rows, right? So if you have one row in your table and it's like here, the coordinator has to go through reading, all of this business before it gets to your one row, and it can respond. And normally, your cluster has a few thousand of these token ranges. Another Amber alert?
So within a V node, like,
yeah, so
V nodes, each one's a separate range query?
Yeah, exactly. So before Cassandra 2.1, each of these ranges were read sequentially, which is especially painful with V nodes. That can take a really long time. It wasn't too bad if you had lots of data in your table, but if you only had one row in your table, it would take hundreds of milliseconds to complete this. In 2.1, it'll estimate how many of these it needs to read to hit its limit, and it'll execute, say, that many in parallel. And then, based on how many it gets back, it adjusts its estimate and tries to fetch the rest. So it's at least a little bit faster, but it's still pretty expensive to do this range query. So range queries are really designed to kind of only be used for big analytics jobs. Say you're running a Spark job or Hadoop. That's really what they're decent at. You don't want to use them for any sort of low latency query. So secondary indexes basically have to do all the same stuff that range queries do, but within each of those ranges, it does this index lookup and then looks into the base table. So with secondary indexes, every node indexes the data that it has locally. So it will, say you have an index on the age of users, it'll have this second table that's keyed by the age value. This is basically a hash index, and that'll store a bunch of pointers into the base table. So it reads this one partition out of the index table, and then it goes in and parallel reads all of the rows that match out of the base table. But like I said, it still has to do all the same range query machinery. So this is why secondary indexes in Cassandra are still really slow. They're not a high performance feature, they're a convenience feature, basically. So I hope I've got my point across that these are expensive. You don't want to use them if you care about performance. Okay, any questions about secondary indexes or range queries? No. All right.
Well, and I think secondary indexes have the additional cost where you have to do the set coverage of all the token range in order to get filled however much data. Well, like if you're looking for everybody who's age 23, you have to cover the entire token range to find that out.
Yeah, yeah.
You have to do a multi-get from the base index to get all that information. So it's an order of magnitude, basically.
Right. So essentially, like the worst case you could use a secondary index on would be something unique like email or social security number. Right. So you're only going to have one matching row, and it's going to have to do all of those expensive queries all the way around the ring until it finds that one matching row. So that's the worst query that you can do with Cassandra. It does work okay if it's something like age, where you'll have a lot of results, and maybe you'll hit your 5,000 limit really early on. In that case, it can work out okay. All right, paging. We're getting pretty close to being done here. I think I've got like 5 or 6 more of these pages. Okay, so paging. Whenever the driver makes a request to Cassandra, it includes this one field that says what its page size should be when Cassandra returns results. This defaults to 5,000 rows. So if you do select star or whatever, a large query result, Cassandra only fetches the first 5,000, returns all of that data along with this opaque blob that's called the paging state. So what the paging state really contains is the last primary key from the result set, the last thing that Cassandra saw. So whenever the driver goes to fetch the next page, it sends the same query, but it attaches that paging state blob. And so Cassandra knows essentially where to pick up the request again. It starts from the last primary key that it saw. So the nice thing about this is that paging state can work with any coordinator in the ring, right? You don't have to send the request back to the same coordinator to continue paging. So this is essentially designed to handle the failure of any coordinator transparently. Like I said, though, the paging state it's treated as an opaque blob. It's not something where you can set it manually in your code to do some kind of offset query. Maybe that'll change in the future, but for right now, it's kind of just designed for internal purposes. Yeah.
Sometimes it'd be nice to say I want 64K back instead of 5,000 rows.
Yeah, that would be nice. Yeah, no, I had it. There's actually a ticket where I discussed this with one of the other Cassandra developers a couple of weeks ago about doing this in terms of size. But let me see if I can remember what the main. So the challenge is Cassandra needs to actually measure the size of all those results, and we don't really have the internal plumbing for doing that very well. That doesn't normally happen until everything's being kind of serialized to be shipped off. So Cassandra would have to start tracking that size as it was pulling results off the disk. The other complication is that there's multiple multiple replicas responding. So you need to try to figure out how to coordinator needs to deal with trimming the results to a particular size. It's something that we'd like to implement, and we might do it internally first as kind of an experiment for, say, for aggregation queries, like you're doing the sum of things. Internally, it would be a lot nicer if we could deal with sizes instead of row counts as well. So if that works out, we'll probably expose that on the external API as well.
And this really helps too, so that previous to paging, it had to marshal all of that data in one gigantic thing. So if you had, say, under query, select star from blah, limit 1 billion explicitly, previously it would be like, oh crap, I gotta marshal all this data in memory and then shove it out to the client. And so if you're already sensitive to the heap limit or whatever, it might kill the server. And that did in some cases.
Yeah, rogue queries could kill your server before paging, but paging usually is decent protection against that.
So yeah, instead of doing that in one block, it'll transparently do that. So it'll send part of it to the client, and it'll just fill up the client at the client side. So
right.
Yeah, I had one. So I had one case where somebody wrote a bug in an application, and something kept failing and kept appending to the end of a row repeatedly for like a couple hours before we figured it out. Yeah. It was like the row of death. If you ever requested that row, you crashed the server.
Yeah. Yeah, that used to be a real problem. Fortunately, paging doesn't completely remove the pain of that, but it's a little bit safer. Yeah.
Does paging assume that the primary keys are being returned in order and you don't insert any primary keys in the past?
So it does assume that the results are always returned in the partitioner order. So that's the order of the hash of the partition key, and then within a partition, it's sorted by the clustering key that you define for the table. So that's one constraint on, say, secondary indexes as well. So any secondary indexes have to be able to return results in that specific order, which can be limiting for some sorts of implementations of indexes. So we might figure out a way to relax that in the future, but for now that's the case. In terms of dealing with partitions being inserted, it does deal with them to the extent that it can. So say you're reading, you read all this range of data, and then before you fetch the next page, you insert a new partition here. It's not going to know that exists. It's just going to resume from here, right? If you insert one that's like exactly on the page boundary, then it can deal with that. So it can deal with it, but it won't it won't go backwards to see new partitions. It's not isolated to where you won't see any new partitions since you started the query. So
maybe a little bit sensitive to that, like for Spark, reading the Spark, it's going to page through, and then it also has its own page mechanism too. But.
Yeah. So if you never mind.
Anyway, it's kind of
good.
Yeah, you could potentially intentionally create some bad cases for Cassandra, but it would be really difficult. All right. Anything else about paging? Okay. All right. So we're on to the replica. So the replica gets this this read request, and I'm basically just going to be describing single partition reads, since this is what most people care about for Cassandra. So it gets this request for some rows for a partition. The first thing it does is it checks the row cache if that's enabled. So the row cache stores entire rows, but basically it just stores a prefix of partitions. So it's configurable. You can specify the number of rows that you want to store from the start of a partition. So say if you always know that you're only going to have one row per partition, that can work out really well. A lot of the times whenever people have wide partitions with lots of rows, say it's like time series data, they usually want to fetch like the 10 most recent events, right? And so the row cache can work well for that sort of a query pattern as well. but it definitely doesn't work for every query pattern. It's pretty rare that we actually recommend that you use row cache. So I don't want to talk a lot about it, but it does exist. So that's the first thing that gets checked if it's enabled. The next thing that Cassandra needs to do is figure out what SS tables it's going to have to actually look at to try and satisfy this read. So it uses as many techniques as it can to try and pare that set of SS tables down. And one thing that it can do is it can look at the clustering key for the ranges of rows that are requested, right? So if it's time series stuff and you requested data between 11 and 12 o'clock, it can look at the SS tables, and there are metrics on what the min and max clustering keys are within that SS table. So say this one has data between 8 a.m. and 2 p.m. We know that that overlaps with the time range that we care about, so we have to read it. But other SS tables may fall outside of that range, and so we can exclude them from the read process. You can also look at things like the max timestamp in the SS table. So this is that conflict resolution timestamp we were talking about earlier. So say if it reads something with a complete row to satisfy the query with a high timestamp, it can ignore SS tables that have a max timestamp that is lower than that, because it knows that they don't have anything that would supersede the data that it already has. Does that make sense, roughly? All right. So the next step to try to cancel out SS tables is something called a Bloom filter. So there's one Bloom filter per SS table. Bloom filters are another really cool data structure if you're not familiar with them. They're probabilistic, and they're a good way to test for set membership. And the response from a Bloom filter, you say, do you contain this thing? And they basically say either probably or no. So if they say no, they're always correct. They'll never tell you that they don't contain something that they actually do. But occasionally, they can give you a false positive and say, yes, I do contain this object, but you go to actually inspect it, and it turns out to not be there. So with Cassandra, it's tuned so that happens about 1% of the time. So we ask the Bloom filter, does this partition exist at all in the SS table? And with about 99% confidence, we figure out if it does or not. So it's really quick, and the way it does it is it essentially runs the key through a set of hashes, and the hashes all map to a very small number. So say for a single key, if you run it through 12 hashes, you'll get about 12 different numbers. And the Bloom filter keeps track. It stacks all of these small number of signatures for every item in the set. And so if you see that all 12 of those numbers have been set, then there's a high chance that that item is actually in the set. That's a pretty bad explanation of Bloom filters. It's really hard to explain a probabilistic data structure without drawing something out, but definitely read up on them. They're cool. So this helps eliminate pretty much all the SS tables that don't contain the partition. So for the ones that do, or that we think they do, the next step is to check the key cache. So the key cache, it takes the partition key and it stores an offset into the actual SS table data file. So for frequently read data, usually this will be present. The key cache is pretty large. You normally have hit rates that are above 90%. So this is pretty common. And so this will allow us just to jump straight into reading out of the SS table if we get a key cache hit. So if we don't, we have to move on to the index. So the index is another big file that's stored on disk, and it contains the position of every partition in the SS table. So it has the key and then the partition, and then the position. So we don't want to have to and we don't want to have to always like scan this huge file on disk every time we do a lookup. So there's a second structure called the index summary that we do keep in memory. The summary is basically just a sample of every 128 item in the index. So together they kind of form this like two-level tree. So we'll look in the summary, we'll figure out approximately where in the index file the actual entry is contained, and then we go and scan the index file, which is on disk, but it's likely to be cached, to find the full position in the SS table. Does that process kind of make sense? All right.
Does it do linear scan? Does it do a binary look?
It does. So it does a binary search on the index summary, and then it finds the starting position for a scan on the index file, and then it's just a linear scan until it finds either the entry that it's looking for or one that's higher than it, in which case it knows that it got a false positive from the Bloom filter. So after it does all this lookup stuff, it can update the key cache as well. So let's see here. I think that's.
And the index summary is adaptable, so the granularity of it is adaptable according to.
Yeah, exactly. The summary. So I said that it's every 128 item in the index. You can configure the range that it can span, but basically they get adjusted based on how often you actually read the SS tables to try and keep them in a fixed amount of memory. All right, so after like 20 slides, we actually get to reading the data part of the SS table. So I actually forgot to update this. This index picture is a little bit simplified. It actually can store a couple of other things about the partition. The first thing is it can store an index of rows within the partition, so that, say if we only need to read one particular row, we don't have to scan the entire partition. We can jump to pretty close to the start of that row and just scan from there. The other thing it can store is information about a deletion of the entire partition, and some statistics about the partition, as well as in Cassandra 3.0, the column names that are present, the clustering keys that are present. So that information it kind of helps to compress the data within the partition and avoid repeating it if that makes sense. So we get that information out of the index. We can actually go to read out of the SS table. The start of the partition can contain some of that same information that I just described. That stuff only ends up in the index if there's a certain amount of data in the partition. And then after that, it's just a bunch of rows. So the actual structure of the data on disk it has changed a lot in 3.0. Before that, it was really designed to match the old Thrift API, which hopefully none of you guys are using, but you know, in modern Cassandra, everything's in terms of CQL and rows. And the old storage format ended up storing a lot of redundant information to maintain this row abstraction. So for every cell or column within a row, it would repeat the part of the row's primary key. There's a lot of repeated information about timestamps and TTLs and all this stuff. So in 3.0, this all kind of gets moved into the beginning of the partition, and there's much less repetition, so it's a much more compact format on disk. If anybody really cares about the format, I can talk more about it, but it's probably pretty boring, so I won't talk very much more about that. So after this is all read, replica can respond to the coordinator, coordinator can respond to the driver, and that's pretty much the entire read path. So I have one bonus slide, but it's on Paxos, which is like I don't know if you guys are up for that, and I don't know if I'm up for that either.
So we probably either have time for some Q&A
Yeah.
or for Paxos. So
Okay.
you technically got to be out of your bike.
Yeah. Okay. I'm gonna go ahead and say my Paxos explanation is gonna kind of suck. So I think we should go with questions instead, just for y'all's sake. So
Maybe just tell them what Paxos is, so that people know that that's a feature or something like that.
So you're gonna rope me into talking. We'll talk about questions. If we run out of questions, I'll squeeze it in. How about that? All right. Questions about any of the read or write path stuff? Yes.
All right. So is there how much of a performance hit is there for starting at the row that's not the first row in the partition?
How much of a performance hit is there?
Move one of my clustering keys into the partition key.
Yeah.
Or not? I don't know.
Yeah. So the question is, reading from the middle of a partition versus the start of it. What's the performance cost or difference? So it's pretty minimal if you use compression on your SS tables, which has been enabled by default for a few versions. The reason is that compression happens in 64K blocks, and so that index into the partition really indexes to the start of these compression blocks, and so you're pretty much just going to be seeking to the beginning of a compression block, decompressing the entire thing, and then reading from that. So when you have to do that, it doesn't really matter where you seek to. If you're not using compression, it is slightly faster to read something from the beginning of the partition. I guess even with compression, it's a little bit faster because you don't have to process and then skip data at the beginning of that compression block. So reading from the very beginning of a partition is always the most efficient read you can do. But with compression, it's probably not a huge difference in reality. Good question.
Are you going to talk about tombstones at all?
Am I going to talk about tombstones? Yeah, so
No.
yes. So I'll just briefly, there's a few types of tombstones. Tombstones are how Cassandra keeps track of deletes. It needs to use tombstones because when you're doing deletes in a distributed database, you have to essentially keep around a record that something was deleted so that other nodes don't accidentally forget about that and revive it. But locally, Cassandra also uses the tombstone for keeping track of what data needs to be deleted or ignored from other SS tables, right? So it might have a tombstone in one SS table and the data that's supposed to eventually delete in another SS table. So there's the tombstones. One is deleting an entire partition, and that's going to show up right here. And that's really the most efficient delete you can do. The second kind of tombstone is a range tombstone, and when you're dealing with CQL, that really only allows you to delete one row at a time. So the range tombstone just says delete all the cells in this row. I think in 3.0 we're going to add support for deleting multiple rows within one statement. So then range tombstones would cover multiple rows. The last type of tombstone is just for a single cell, right? So you can delete one column out of a row, and so there's just a special cell that just marks that that column has been deleted. So that's the three kinds of tombstones. Some people's data models have problems with lots of tombstones, especially if you use Cassandra like a queue. So it's definitely something to read up about. Since we're close to being out of time, though, I don't want to talk too much about that. Yeah.
I wanted to ask what kind of effect is static columns and effect on the repack?
Okay, so the question is what effect do static columns and UDTs have? So I'll answer UDTs first because it's simplest. They basically have no effect. It's basically it's just a way of encoding the data on disk. It's basically the same as a tuple or anything else. So really, it doesn't affect the read path too much. Static columns, those are within a partition. They're shared across all rows in the partition. So I didn't show it here, but in 3.0, all of your static columns are basically going to get crammed in right here. And so anytime you read from the partition, it's always going to read those static columns and then go read the row. So that's how static columns tend to affect it. All right.
What kind of compression do you get when you compress the data?
What kind of compression do you get? So prior to 3.0, you get pretty good compression ratios. I think it's pretty typical to see it reduced to about 25% of the original size. That's both because Cassandra is storing a lot of redundant information, and in a database, a lot of the values you store tend to be somewhat redundant as well. So it's usually pretty compressible. We use compression algorithms that are generally easy on the CPU, so they're not trying to compress it as much as possible, as just however much compression we can get really cheaply. You can specify a custom compressor. I don't think anybody does. With 3.0, since we started storing much less redundant information, compression really doesn't save you very much, so we're thinking about disabling it by default for 3.0. All right, looks like I don't have to explain Paxos.
I don't think we have time for Paxos, guys.
Yeah. All right. Well, thank you guys for coming out. I enjoyed giving it a talk.
Needed a parking validation. Thank you. Hopefully I'll see you guys next month. Grab some more pizza, t-shirts.